Okay, so apparently Facebook has an AI that can do advanced math. Let's take a look. We've got an integral here that can be solved. It is an integral. It's represented as a differential equation, but it's an integral. Y's derivative is this expression here, and looks like they have an AI, a neural net, that solves it and determines that this is in fact the solution. Let me talk here about these guys at Facebook AI Research in Paris that developed a neural network to do the symbolic reasoning. It's an article on technologyreview.com. We're going to talk about it here a bit. So let's see here. They compare it to commercially available solvers, Maple, MATLAB, Mathematica. These solvers use an algebraic approach worked out in the 60s by the American mathematician Robert Risch. Risch's algorithm is huge, running to 100 pages for integration alone, so symbolic algebra software often uses cut-down versions to speed things up. And they say they've tested their neural network. Their model obtains close to 100% accuracy, while Mathematica barely reaches 85%, and MATLAB and Maple perform less well than Mathematica. Well, first of all, I do not believe that any of these programs, Mathematica, Maple, or MATLAB, implement the Risch algorithm. As far as I know, Axiom is the only really commonly available software, and it's open source, that implements Risch's algorithm. I'm not even sure I'd say your Risch's algorithm is huge. Well, sort of. I mean, I've got his paper right here. Let's take a look at it. Let's open it up with Ocular so we can annotate it. Here's his paper. It's only 4 pages long, but it is dense. I've been studying this thing for years. Let's just take a quick look here. The most surprising aspect of the integration problem is the fact, implicit in the above, that it reduces to the problem of bounding torsion on the Jacobian variety of an algebraic curve, whatever that means. And then he goes down further here, bound for the torsion. When integrating a given elementary algebraic function, one only needs to be able to find the bound for an explicitly given curve. And then he outlines a method of doing that. Down here, talks about good reduction. Some assertion follows from Shimura's result. I've spent almost 20 years, and I still don't completely understand all of this. So not quite 100 pages, but a lot of background is required to grasp his algorithm. Let's take a look here. Let's see. Let's look at these different programs and see who can do what. First of all, let's take a snapshot of this thing here. How do I do that? I think this. Yeah. Alright. We'll just stick it down here. Alright, so here's our problem. And here's the Facebook AI's solution. This is what Facebook came up with. So it's Facebook AI. That's what they came up with. So let's try Mathematica. Wolfram Alpha, which I believe is pretty much Mathematica under the hood. So we take this whole thing. I've already typed it in. You can type it in if you want. Type us all in, tell it to input, and it says no result found in terms of standard mathematical functions. So yes, it certainly seems that Wolfram Alpha, and I would suspect probably Mathematica too, cannot simplify this expression. But now, as I said, if you really want to do this, the best way, I think, really is Axiom. That's going to be your best bet. This is, as I said, open source. So what do we got here? We've got our root. Let's take our root, copy, paste. I want this to be in the Axiom language. This is a colon equals. Okay. Let's take this numerator here. There's that. And then I think, so yeah, this is all we need to do here. We want to integrate the numerator over the square root, which is what this is. The numerator over the square root right here. Right here. Yeah. So let's see what Axiom. Axiom comes up with an arc tangent, and that actually is a correct answer. It's just in a different form from the version that Facebook came up with. So let's stick this up here, and this is going to be the Axiom version of the output. So we have an arc sine, and we have an arc tangent. So let's see. First of all, let's just take a look at why these two are the same. So if we want to compare arc sines to arc tangents, how can we do that? Let's do this. Let's take a look at, just say sine squared of, let's just say some angle plus cosine squared. And I think I'm going to just divide through by sine squared. So we get 1 plus cosine over sine, which is cotangent. And I'll just write it in this form like this. So this is a relationship between sine and cosine. And let's see, what do I want to do here? I think I want to write tangent in terms of sine. So tangent squared equals 1 over sine squared minus 1, and I will invert and get this. So actually it's 1 over that minus 1. Let's multiply through over here by just sine squared over sine squared. And we'll get sine squared theta over 1 minus sine squared theta. Take the square root of both sides, and then we'll get tangent equals sine theta over square root of 1 minus sine squared theta. So this is a relationship between tangent and sine. So if we have something that is, let's say f, let me just change to a different color here and say if we have f equals arc sine over here. Yeah, if we have arc sine of an expression, we'll call this g. Let's see, g is arc sine of f. And if g is the arc sine of f, then the sine of g is f. And that means here's this relationship between f, so the tangent of g is going to be equal to this thing, this expression of the sine, so it's going to be f over the square root of 1 minus f squared. And then I want to take the arc sine, or the arc tangent of this, and say g is the arc tangent then of f over 1 minus f over the square root of 1 minus f squared. So if this relationship holds for arc sine, if g is the arc sine of f, then g is also going to be the arc tangent of f over the square root of 1 minus f squared. And then the question is this thing here, the 4x to the fourth minus 4, this would be g, f, inverse sine of f. Okay, and we're looking at the tangent. F is in the numerator, and you see there it is. It's right there in the numerator. Right there's the numerator here. That's identical to the sine form. And the question is this thing in the denominator the square root of 1 minus f squared? And it shouldn't be that hard to verify this. What is it? 4 times x to the 4th minus 14x cubed plus x squared. And what do I want to do? Square it. And was it add 1 or subtract 1? What was it? 1 minus this. And yeah, you see here that this thing here, this expression under the square root, is identical to this expression here. So in fact, the Facebook AI and Axiom come up with the same expression. Well, no, they come up with the same. Both come up with the correct answer. It's just done in two different forms. I mean, I would certainly argue that the Facebook AI form is simpler than the one that Axiom came up with, but they're both mathematically correct. Now, the next thing I want to look at is Sage, which is the program that I've spent most of my time the last couple of years working on. So this is a development version of Sage. It's not quite out yet. You see, it's 9.0 beta 9. Version 9 of Sage will be out probably around February of 2020. But this is a pre-release. So first of all, let's see if it can just do. There's the root, right? And there's the thing inside the root, which is this whole expression here. This whole thing here. That's the thing inside the root. And then the numerator. Here's the numerator. So can Sage integrate the numerator over the square root of the root by x? And it cannot. We can factor out a 2. You see there's a 2 that can come out of the numerator, but that's about it. You can't get much further than that with its standard integration library, which I'm pretty sure is based on Maxima. Sage works by pulling a whole bunch of other, well, not totally, but a lot of other mathematical packages, a lot of programs are used. Sage will borrow freely from other programmers by just pulling them into its distribution and calling them as subroutines. And I'm pretty sure it's using Maxima to attempt this integral, and it does not compute. However, we can step through the Riesz algorithm, and in some sense that is, even more interesting than just sticking it into a machine and it just spits out an answer. We can look how the Riesz algorithm works. So, first of all, we note that this exists on an algebraic curve. Let me make another. Let me do this here. Let's just step forward 2 screens, and let's grab another copy of this. No, not that. Not that. This, the original problem. So what do we have here? We have a function on an algebraic curve. We have the integral of 16x cubed minus 42x squared plus 2x over, I'm just going to say y dx. And y is this whole square root of this thing here. So I say I'm going to square y. Y squared is negative 16 HDS 112 AC, all this stuff here. Just write down. It's that. So what we have here is we have an algebraic curve. We have a polynomial relationship between x and y, and we have just a rational function, ratio of polynomials in x and y. So this is an algebraic function, a rational function on an algebraic curve. So we're going to use Sage's function field code, which is this is a function field. It's a function field on an algebraic curve, and we're going to use Sage 9's new algebraic function field code to attack this problem. So how do I want to do that? First thing I want to do is I'm going to create just a rational function field in X. I'm going to use QQ bar, the algebraic field. That's a lot of ways it's the most, it's the simplest. It might not be the fastest, but it's the simplest. It's the algebraic closure of the rational. It includes all square roots of all kinds. It's all algebraic numbers. I'm going to set its display format to be radical, so it'll print stuff out in nice, like square root notation if it can. Not all algebraic numbers can print as radicals, but if it can print as radical now, it will. What do I want to do here? I'm going to make an extension of OR. I'm going to add so now it's a polynomial ring in R and Y, and I'm going to, yes, I'm going to now restrict by my root, my polynomial equation. So I get a function field in Y defined by this polynomial being equal to 0, which is this polynomial here, just with the whole right hand side moved to the left hand side and leave 0 on the right, and we get this. So we now have an algebraic curve. I have y, and if I take y squared, I actually get this. So y is the square root of this polynomial, at least on this algebraic curve. And now what do I want to do? Well, now I want to look at the numerator. I'm going to put the numerator into this field, R, and I'm going to divide it by y. So that is going to give me this. It just normalized it by multiplying through by y, and we just got this fraction in x times y. It is the numerator over y. If you take a look at this, and I want to multiply this by x differential, because it isn't just a function, it's a differential. Just got to add that dx at the end. And I'm going to call this d integrand. And now I'm going to ask the machine where are its, well, actually, where are its zeros and its poles. That's what I'm going to ask it to compute. You know, why do I care about while it's doing that? I'm going to take this dime and roll. See how long this doesn't get too long, I don't think. I hope. Might have to think a little while to compute those radical forms for QQ bar. There we go. See these things, these square roots. You know, we actually don't really care about this. All I care about are the first two, the negatives, the poles. I don't care about the zeros. Why? Why do I mean, we're getting into really the essence of what the Riesz algorithm is. Well, if you consider what happens, we try to integrate just something like, I don't know, whatever x times x plus 1 or something. We typically split this apart until there's some constant a over x, this is a dx here, plus some constant b. We do a partial series expansion. We're interested in where the poles are of this function. And in fact, you can even look and you could say, well, let's see, what about something like, you know, x squared plus x? Well, actually, if we consider infinity, if we look at this from the standpoint of projective space, these are actually poles at infinity. This function has a pole at infinity. When x goes to infinity, this expression becomes infinite. So we got finite poles here and an infinite pole here. And if we put the whole thing in terms of projective space, we were to look at something like, I don't know, something like this. We could expand this out and do a partial fraction. It would be some number a, whatever the partial fraction would be here, x plus 1, and then we could say this would be 1 over x, and this would be 1 over x squared. So we could see, we could write this whole thing out in terms of poles, either finite poles here at x, or 0 and -1, or infinite poles at infinity. And in fact, that is one of the key ideas in the Riesz algorithm. And really, we just want to look at our poles here, and we just want to find out, we just look at how this function behaves at its poles. So I'm going to construct dpoles is just going to be, I need to save that divisor, call it D. And then I'm going to do dpoles, which is just, I just pulled out these two places where the negative sign, where I have first order poles here. And then I want to run a completion. I want to basically do a series expansion at each of those poles. And let's see here, for C and completions, and this will print out the series expansion. I asked for just for the series expansion up to first order precision 1. I could have done longer, but well, first of all, let's just take a look at. No, I didn't define integrand. Oh, I defined d-integrand. I also want to define integrand because I can't do series expansions of differentials. I have to explicitly write the expansion of the integral times the expansion of x and then take its derivative. This is essentially the series expansion of dx, and this is the series expansion of the integral here. And let's just make this a little bit longer. Maybe do a third order. If I ask for a third order series expansion, I can see I get a little more information here. I got here it's just the pole parts of it, with just something of order 1, some constant term here. And now I've asked for more precision in my series expansion. Now I got the polar part, the 1 over s, the constant part, the s term, and there's all that higher order stuff of s squared. And I could ask for a higher degree expansion. These are some of the new features in Sage 9. You can do these kinds of series expansions on an algebraic curve. So what am I interested in here? I'm interested in this polar part right here, this stuff. I've got two places. Let me just make a copy of this here. Got these two places. Go down here and put them in here. Tools, not rectangle, hand tool. There we go. No. Let me turn off the rectangle. How do I make this thing? Alright, let's just do this. And let's paste it again over here. There we go. Okay. So what have I got here? I've got two poles here and here. And then on these two, I've got these two series expansions right here. Right, and these give me my two series expansions. So at each of these poles at infinity, both these 1 over x, these are poles at infinity. They're not in a finite place. And at each of these, I have got a polar series expansion. And the fact that it is an s to the -1, it's a 1 over s, that means this is going to give me a logarithm. Because if you look at what happens when you integrate 1 over x, first you get log x. Whenever you have if you had a 1 over x squared, whatever, this is going to give me -1 over x plus c, right? Whenever I have and the same occurs in these algebraic curves, it does just simpler rational functions. Whenever I have a higher order pole in the denominator, like this, it's going to give rise to a rational functions in the integral. Whenever I have a first order pole, it's going to give rise to a logarithm in the integral. So what I've got here, set this aside, what I've got here now, I got two first order poles, and these are the only poles. All these other pluses are zeros. These are the only poles of this differential. And in fact, I don't care what the zeros are. The poles give me enough information to compute the integral. I've got these two poles, both in infinity, and one has a series expansion with a coefficient of 4i, and the other has an expansion with negative 4i. So what I now want to do is I want to see if I can find a function that has a 0 on the second one and a pole on the first one. And why would I want that? Well, let's take a quick look again at logarithm. How does like log x, yeah, let's put log x. How does log x look if we plot it? What does log x look like? Yeah, it should be, that's what color can we use here? Let's go with green. Log x looks like this, right? This is what log x looks like. So log x has two poles. The function logarithm is pole as x goes to 0 has a negative infinity here, and then as x goes to positive infinity, it has a positive infinity here. So what happens here is, when we look at the values here, these coefficients, this 4 and this negative 4, the 1 is going to, we want 4i times a 0 at the one and a pole at the other, because one's positive and one's negative. And we want a 0 at, actually they're going to flip signs, because when we do a, like if you take a, what do we do here, like the differential, let's just do a differential of a log. If I just do a differential of the logarithm of f, what am I going to get here? I'm going to get f's derivative over f here. So this derivative here is going to cause a negative sign to appear in my whatever power this is, it's going to be a negative power. Whatever power it is, when it differentiates, it's going to go down 1, and it's going to introduce a minus sign here. So I actually want to pole at this first one and a 0 at this second one. So if I go back up here and I now say, what do I want? I constructed d poles. Here we go. And if I say I want d poles, first of all, let me just take this out. These are my two poles, and I just changed around a little bit here. See, they were both negative here. They were both poles. I pulled them out and I made one negative and one positive. I made the first one negative, because that's this one here that I want to be a pole, and then this one, because the signs change, I want this one to be a 0. So I'm going to take two of these, and then I'm going to ask Sage, is there a basis for this function? I mean, are there poles that can do this? Or is there a function that matches up these poles? The answer is no, there is not. And now we're starting to get a little bit into the Riesz algorithm here, because I can just keep going with this until I hit 1, and in fact, I found one. And why can I do this? I can do this because if the logarithm of f squared is 2 times the logarithm of f. So in fact, if I don't have a function that matches the poles and zeros that I want, I can look to see if can I find a function that matches twice the poles, twice the strength of the poles and zeros, which would be the square of it, and then what this would be this, except that when I'm dealing with these curves, these algebraic curves, I might have a case where I've got a function here that exists on the curve, but its square root, which would be this f, does not exist on the curve. And that's the case here, that I've got a function now that exists on this curve. So I've actually got basically my answer right here. Let's first of all, let's just take a screenshot of it. And where am I going to put it? I'm going to put it right here. And what does this mean? It means that my solution then is going to be 4i times 1/4, because I needed to go up to a 4 here, and you can see immediately there's going to be a cancellation. But I got this extra 4, like this becomes this 1/2 here, so I got 1/4 here times the coefficient here, which is 4i, times the logarithm of y minus, let me see, there's a I there, 4x to the 4th plus 14x cubed minus x squared. And then these two cancel, and I'm just basically left with this complex logarithm. So let me make a copy of this, and let me put it here on this page and work with this a little bit. So what can I do here? What do I do? This is another. This is just like we had here. Facebook gave it to us as an arcsine. Axiom gave it to us as an arctangent. Just kind of crunching through it manually with Sage gives us this thing as a complex logarithm. And in fact, these are all valid forms of the same thing. You can see this is somewhat similar to if there's a similarity here with this Facebook. There's a similarity here with this Facebook expression. And if we put it here, and the question is, are these two the same? And they are. How can we know this? Let's look at what happens here. E I theta equals I sine theta plus cosine theta, and I want that written in terms of sine theta. So we just change my cosine theta to be 1 minus sine squared theta. And now I'm going to switch to arctangent. So let's just call now the angle becomes the arctangent of f. This becomes Ix plus the square root of 1 minus Ix. I'm going to take the logarithm of both sides. I'm going to get I times the arcsine. It's going to be equal to I log x plus 1 minus x squared. Bringing the I over, I get this. I am pretty sure now if I bring the sign in here and have to invert this, I'm pretty sure, without going through all of the algebra, I think what happens is this is just the inverse of this. And now the question is, do I have it in this form? Or perhaps I wanted this to be me. Maybe it's this one that negates. I'm guessing a little bit on this, but I'm pretty sure this works. So, yeah, I think this is what we've got here. We have negative Ix, and there is our x right here. Actually, I used f here. This should be f. This should be f. So I used f. This should be f. These are all f's. So I used an f here. These should be f's. This is f. Okay, this is also f here. Then I've got negative if, and there's my negative if right here. And then y, the square root of 1 minus f squared is in fact the original root we started with. Is it 1 minus this thing squared? And did we already check this? Maybe we did. Yeah, I think this is. Did we check this for the? Let me check for the arctangent. Let me check for the arctangent. Yeah, I already checked this. That this thing squared, 1 minus this thing squared is the original root we started with. So right. So this is this y, which is the square root that we started with. This thing is the square root of 1 minus this thing squared. So we see that this complex logarithm, I times this logarithm, is in fact the same as the arc sine here. The arc sine of f is, I dropped the negative I here. Right here there should be a negative I. Oops. Yeah. Almost done. There. Yeah, the arc sine of f is the same as negative I times the logarithm of this expression, and that's the expression we've got here, which is the same, different form, but the same as, a copy of that. Let's just go back to the beginning and paste it in. We're going to say, I'm just going to call this Sage by hand. That's that. And these are all identical copies of the same answer. Saved by the Bell. Hope you enjoyed it.